Welcome to Lecture 7.5, 3 PDEs on a disk. Last time, we saw that in polar coordinates, the Laplacian operator is no longer the sum of the second derivatives. Instead, it's more complicated. It's 1 over r ddr plus d squared dr squared plus 1 over r squared d squared d theta squared. So that's why we call it with this delta instead of del squared. Here's a slightly simpler way to write it if you prefer. The eigenvalues and eigenfunctions of this operator for the unit disk, that is if r goes from 0 to 1 and theta goes from 0 to 2 pi, the eigenvalues are omega nm squared, and the eigenfunctions are of the form cosine of n theta times jn omega nmr and sine n theta times jn of omega nmr, where omega nm is the mth positive root of jn of r, which is the Bessel function of the first kind of order n. So slightly differently, if you have a disk of radius a instead of 1, then you divide by a, you have omega over a squared for the eigenvalues, and then you have omega over a in here. In this lecture, we'll solve boundary value problems for our three favorite PDEs. We'll start with Laplace's equation and inhomogeneous boundary conditions, otherwise it's quite boring, the heat equation, and the wave equation. These arise naturally when solving, for example, the heat equation over a circular plate or the wave equation over a circular drum. Our first example is Laplace's equation. So let's solve the following boundary value problem for Laplace's equation in polar coordinates. So Laplacian of u equals 0, and now we have these two boundary conditions. This is the first one that tells us what the, think of this as temperature, is along the boundary of the disk. So we have a disk like this, and suppose that the temperature is something non-uniform along the boundary. This, of course, is going to project down onto the boundary like this. And so, of course, the minimal surface here is, think of making a wire out of this and dipping it into a soap bucket, and you're going to get some, think of this as like a potato chip surface, or again, a soap bubble surface, something like that. And now we need periodic boundary conditions in theta, of course. Okay, so let's solve this. So let's assume that u of r theta equals big R of little r times big T of theta, as before. And we're going to plug back in. So if we do this, we get, now I don't need to write the derivatives, we've done this enough. I'm just going to write these three terms. This first term is r double prime times t plus 1 over r times r prime times t plus 1 over r squared times r t double prime equals 0. Now let's divide both sides by 1 over r squared rt. I don't need to do that on the right because we have 0. And what we get is, well, let's do term by term. So this term here gives us r double prime over times little r squared times over r. So let's write that down. Little r squared, big R prime over r. Then the second term is r times little r times big R prime over r. R times big R prime over r. And then this last term, oh, the r's are going to cancel and the r squareds are, so we're going to let's move the t's over to the right hand side, and we get this equals negative t double prime over t. So this, of course, is a function of r, does not depend on theta, and it's equal to this function of theta, it does not depend on r, so together that means this quantity must be a constant. I'm going to call that lambda. Not negative lambda, because I actually want this equation to naturally look like sines and cosines. Okay, so let's write down what we get. So we have t double prime equals negative lambda t. We also have a boundary condition from this periodic condition here. So recall that this tells us that, so this is big R of R times t of theta plus 2 pi, and that equals r, or u of r theta, which is big R of R times t of theta. So that means that these r's cancel and we get t of theta plus 2 pi equals t of theta. So we get t of theta plus 2 pi equals t of theta. And we've seen this before. We know how to solve this. We know that lambda equals n squared, and Tn of theta equals an cosine of n theta plus bn sine of n theta. I previously liked to not include the an's and the bn's in these eigenfunctions, but here we have two constants, so we really can't avoid it unless we want to break these into two different eigenfunctions like we did before. Remember fn and gn, one of them is cosine, one sine, but let's not do that. Okay, the next equation that we get is in R. So we said we multiply R on the right, we get that little r squared big R double prime plus little r big R prime. And now I'm going to move this to the left-hand side and write that as minus lambda. Well, we know what lambda is. Lambda is n squared. So minus n squared r equals 0. And we don't have any sort of boundary condition for this. Okay, so this here is a Cauchy-Euler equation. You remember that? When we studied power series solutions of ODEs, the very first case was, well, we didn't actually need a power series, was when for each derivative of R, and it was y in that case, it was an x here. So here we have one derivative, and we make up for it by multiplying by r. Here we have two derivatives, and we make up for it by multiplying by r squared. Well, actually, before we do that, let's do a simpler case when n is equal to 0. So because that's going to be easier. So when n equals 0, we have a simpler ODE. We have r, so this is case 1, r squared times r double prime plus little r times r prime equals 0. This looks like a second order ODE, but really what you can do is you can change variables. You can say, oops, let's change that. Let's let y be equal to r prime, and so y prime equals r double prime, and then this becomes r squared y double, it's not double, r squared y prime plus ry equals 0. Do you remember how to solve this? Please tell me you do. I'm not going to actually do it. I'll get you started and I'll let you finish it and I'll tell you the answer, because I don't want to spend tons of time doing this sort of thing at this stage. So remember, separate variables. Different type of separate variables than what we're doing here, but the same theme. So dy dr, so we can move this to the right hand side, divide by r squared. We get dy over dr equals negative, let's see, what do we get? Negative y over r. I don't know, maybe I'll do this. dy over y equals negative dr over r. And we want to integrate both sides. And we get the natural log of y equals negative times the natural log of r plus constant c. Then we exponentiate both sides, and we get y equals, let's see, so e to the c times e to the negative natural log of r, which is, let's call that big C, times e to the natural log of r to the negative 1, which is c times natural log of r is r, so times 1 over r. Okay, so that's what y is. And so what is, so if y is equal to 1 over r, and that's the derivative of r, then r is the integral of y, which is, I'm going to say c times the natural log of r plus d. So this is what r is. Now, we really don't want, or in this picture here, we're assuming that the function is defined on the whole disk. So I really should add, I don't have a boundary condition here, but I should say that r of 0 is finite. And the natural log is not even defined at 0. So what we need is, we need that c is equal to 0, since, and so what does that mean? That means that so we get here that r of little r equals the function d. Do I want to call it d, or do I want to call it, how about if I call it a? Because think of like a naught over 2. So I'm going to call this a. It's a constant. Okay, so that's this case. But the next case is when n is positive. And in this case, we have what I said before. This is a Cauchy-Euler equation. So we have a Cauchy-Euler equation. And remember how we do this. We always assume that r of little r equals r to the k. I think before I did x to the r, but now r is our variable. So r to the k. So if we do this, r prime equals k r to the k minus 1. And r double prime, let me put a line here just so you can sort of differentiate between these parts. And r double prime equals k times k minus 1 times r to the k minus 2. So if we plug this back in, we plug these guys back into here, see what we get. We get r squared times k minus 1 times r to the k minus 2. The first term. Then we have an r times a k times an r to the k minus 1. This is equal to r prime. And then we have a minus n squared r to the k, and this is equal to 0. And if you simplify this, so how does this simplify? So we have a k squared. So first of all, we have an r to the k in every term here. Now we have a k squared, we have a minus k, we have a plus k, and a minus n squared. So this tells us this is k squared minus n squared times r to the k equals 0. So remember, r, this is our variable. So that tells us that k squared minus n squared is 0. And that tells us that k equals plus or minus n. So we figured out what k is. So thus, in this case, we have r is c1 r to the n plus c2 r to the minus n. But again, we need our function to be defined at 0, and this is not defined at 0. So let's say that r of 0 being finite tells us that c2 equals 0. So this term goes away, and here's what we have for r. So I'm going to call this Rn. So now what do we have? We have a solution. So thus, for each n equals, let's see, can we start at 0? So when n equals 0, we have a constant term here, just an, and or a naught, and we have a constant term here. So we have a constant term. So I'm going to say, sure, when n equals 0, 1, 2, etc., we get a solution un of r theta equals, how do I want to write this? R to the n times an cosine of n theta plus bn sine of n theta. There we go. So that's a solution for each n. Think about what that means up here. So radially we have, so it's, well, let me hold off on that thought. So that means that the general solution is going to be u of x, oh sorry, we don't have an x here, do we? U of r theta is the infinite sum from n equals 0 to infinity of, well, of this. Yeah, we just put a sum in front. So it's r to the n times an cosine of n theta plus bn sine of n theta. So this describes every possible solution to Laplace's equation when we haven't specified the boundary. So it looks like this. Now, what have we not done yet? We have not used the last boundary condition. We've used the periodic ones, so let's do that now. So I'm running out of room here. I should not have done this whole problem here, but I think it was worth it, I guess. So I can find room. Let's plug in r equals 1. Use the last boundary condition. And look what happens when we do that. Plug in r equals 1, the r to the n goes away. It becomes 1. So when we do this, we get u of 1 theta is n equals 0 to infinity of an cosine of n theta plus bn sine of n theta. I really should have pulled this out as, maybe I can still do it now. Let's call this a naught over 2 plus, and then start this from 1 to infinity. And I'll do the same thing here, although I've actually kind of run out of room. So I can do that. I can stick in an a naught over 2. And this is equal to h of theta. So quite literally, these an's and these bn's in our general solution, what they should be, when we plug in the last boundary condition, these are the Fourier coefficients of h of theta. That's exactly what they are. Our second example is the heat equation on the disk. So let's solve the following boundary and initial value problem in polar coordinates. So ut equals c squared Laplacian of u, that's the heat equation. We have Dirichlet conditions. We're fixing the temperature to be 0 along the boundary. Of course, we have periodic boundary conditions in theta. And then we have an initial condition. So we have a disk, and I don't know what the initial heat distribution is. We know it's fixed at along the edges, and so what's going to happen over time, this is going to just spread out and dissipate and go to 0. So let's assume that u of r theta t equals f of r theta times g of t. And let's plug in. And again, I'm not going to do the individual derivatives. I think we can do this all at once. So ut, the left-hand side, is f times g prime. And then the right-hand side is c squared times Laplacian of f times g. So let's divide both sides by c squared fg. And what we get on the left-hand side, the f's cancel, and we have g prime over c squared g. The right-hand side, the c squareds cancel, the g's cancel. We have Laplacian of f over f. So this on the left is a function of time, not of position. It's equal to this function of position, not of time. So it must be constant, and it's equal to negative lambda. Okay, so we get two ODEs. Or we get a PDE and an ODE. First, the PDE is Laplacian of f equals negative lambda f. That's the Helmholtz equation. And I should add the boundary condition. So this boundary condition here tells us that f of 1 theta times g of t equals 0. And that's so g of t is a function, f of 1 theta. It's a number or a function. But if it's 0, then this has to be a number and it has to be 0. So f of 1 theta equals 0. So we get that f of 1 theta equals 0. And we get that f of r and theta plus 2 pi equals f of r theta. Like I said, we've seen this one in the last slide. I don't need to rewrite it again. I'll just write it here. So periodic boundary conditions in F. And we also have that g prime equals negative c squared lambda g. So these are our two equations. And we solved this one in the previous lecture. So please watch that if you have not already. So we get that, we know what lambda is. We know that lambda nm equals omega nm squared, where these in omega nm, I don't know if I see that. This is the nth root of the nth positive root of the Bessel function Jn. Okay, so that means that, well, maybe I should have written this is equal to negative c squared omega nm squared times g. And this tells us, well, actually, I didn't tell you what f is, so f, how do I want to write this? Because I was thinking this because I have an f here. Yeah, so I'm going to say that f, and I may regret this choice of letters later, we'll see. So the corresponding eigenfunction. Yeah, you know, I'm going to call this big F. You'll see why in a moment. This is ANM cosine of n theta Jn of omega nmr plus BNM sine of n theta Jn of omega nmr. So that's the eigenfunction for this. Because remember last time we called this first part FNM and this second part GNM. That's why I wanted to call this a capital, because I want to do that again. So now down here we have, I'm going to call this capital G and M of t is e to the negative c squared omega nm squared t. So here I'm not putting a constant in because we will put it in later. Again, I have 2 in here. I can't really pull both of them out. Okay, so we can do what we did before, and we can call this thing an. Oops, let me do this instead. Let me call this thing without the constant FNM of r and theta. I don't know if I'll actually use this, but I'm going to call this GNM of r and theta. So I apologize if this G looks too much like that and this F looks too much like that. That's why I'm using capital F here and capital G there. Okay, so what's the general solution? So the general solution is the sum over all n and m. So n goes from 0 to infinity, because we could have a constant term. And then m, remember m, these are the roots of the Bessel function, so the positive roots, so we start with 1. And I'm going to call this un, let me call this unm of r, theta, and t. And so I should probably write out what that is. So I'm going to say for up here, for each n and m, we get unm of r theta t, which is anm f nm. So it's this thing here times the exponential function. So I'm going to say plus bnm gnm times e to the negative c squared omega nm squared t. I could have written that out, but I feel like it's messy enough as is. So the general solution is the linear combination of these. I'm not putting a constant in front because we have these constants embedded in there, okay? But I will write what that is. So this is the sum from n equals 0 to infinity, from m equals 1 to infinity, of ANM cosine of n theta Jn of omega n r plus Bnm sine of n theta Jn of omega nm r times e to the minus c squared omega nm squared t. So it's basically a superposition of all of these over all possible n's and m's. Okay, so this is the general solution. What have we not done yet? We've used the Dirichlet conditions. We use that here. We use the periodic conditions. We have not used the initial condition. So this describes all possible solutions to the heat equation before we specify the initial conditions, only subject to that it's 0 at the boundary. So now let's use the initial condition. So u of r theta 0. So what happens when you plug in, I guess I missed my, oops, let's do that again. Use initial condition. U of r theta 0, there, no theta there. This is equal to, well, the infinite sum, I can write that out. N equals 0 to infinity, m equals 0 to infinity. What do we get now? Well, the exponential function goes away. We just get this is a Fourier Bessel series. So we have ANM cosine of n theta Jn of omega nm r plus Bnm sine of n theta times Jn of omega nm r. This is and we have to set this equal to hr of theta. So now I am indeed going to use these f's and g's. So I'm going to call this, again, this is f and m, and this is going to be g and m. Okay, and so to set these equal, well, how do we find a Fourier Bessel series of H? Well, by orthogonality of the eigenfunctions, we know that ANM is the inner product of H with FNM, like we did in the last lecture, over FNM and FNM. And we know that BNM, this coefficient, this is just the projection of this onto that corresponding term, GNM. So BNM is equal to HGNM over GNM, GNM. And I'm not going to actually do this for example, but you saw this in the last lecture. These are things we can do. We have nicer formulas for this. Finally, the last thing I want to say about this is, let's suppose that we had non-homogeneous boundary conditions. Suppose that the boundary of, so instead of this, suppose that we have this disk here, but I don't even know how to draw this, but the boundary was this wire like this, and then our initial condition was like that. What's going to happen over time? It's going to flatten out. How would we solve that? So in that case, u of r theta t would be the homogeneous solution. So you basically make it homogeneous, and then you find the steady state solution, and you add those together. So we just solved the homogeneous problem, so we know how to do this. This is example 2. And in the previous example, Laplace's equation and the disk, we saw how to do that. So we know how to do both these pieces. If we were to have a heat equation in polar coordinates with inhomogeneous boundary conditions, we can do that as well. Just add these things together. Finally, our last example could model, say, the wave equation on a drum. So let's solve the wave equation with the same boundary conditions as before. If you have a circular drum, it makes sense that it's going to be clamped down along the edges, or along, I should say, the edge, because it's circular. You need periodic boundary conditions in theta. But now we need two initial conditions. We need both the initial position of the drum and also the initial velocity, because we have two time derivatives. So this is almost the same as the heat equation. So I'm going to say, write down, this is same as the heat equation. Almost. Let's just write down the differences. So we will assume that the solution separates as before. So u of r theta t is f of r theta g of t. We plug this back in, we separate variables. The only difference is we get an extra time derivative of g. So we have g double prime instead of g. So we've seen this enough that I think you can buy that the first equation is the Laplacian of f equals negative lambda f. So it's Helmholtz's equation in polar coordinates. F of 1 theta equals 0, and f of r theta plus 2 pi equals f of r theta. And then the second one is g double prime equals negative c squared lambda g, which is negative c squared omega nm squared g. So again, as before, everything in f is the same because the spatial derivatives are the same. The only difference is this, we have a double prime instead of a single prime. So how does that play out? So that means that g, let me call that a big G as before. I think I should call it a big G. Let's see, big G and m of t equals, now here's what I'm not sure what to call it, because I'm going to have multiple coefficients. So let me call this a and m prime cosine of c omega n m t times or plus b n m prime sine of c omega n m t. So you look at this, you think that's sines and cosines, and the frequency is c times omega n m. And now I'm calling this primes because let me write down what f is, just to remind you. So f of nm of r theta, so this is, I'm going to call this big A n m times cosine of n theta times jn of omega n m r plus bnm sine theta jn of omega n m r. So this is f and this is g. So our general solution, well, let me say for each n and m, we get a solution u n m of r theta t, which is a product of these things. So f n m r theta times g n m of t. So if you take the product of these, you actually get four coefficients. You get these two, and they all arise. So if you FOIL this out, you get four terms. You get a cosine times a cosine times a Bessel, plus a cosine times a sine times the Bessel function, plus a sine here times a cosine there times the Bessel function, and a sine here and a sine there times the Bessel function. So I'm going to actually see how I can do this notationally. So the general solution, it's not going to be actually that bad, or I don't think it is u of r theta t. So the sum from n equals 0 to infinity and from m equals 1 to infinity of u n m r theta t. So it's the infinite sum of these guys up here. So I could write this as this infinite sum. Let me see if I'm doing this correctly. So a n m cosine of n theta. I don't know if I'm going to have room here. Jn of omega n m r plus, and then what did I call this? B n m sine of n theta. Oh, look what I forgot up here. I forgot my n theta. So I'm going to stick put an extra. You see that? Sine of n theta? Yeah, I think you know what that is. Sine of n theta times jn of omega n m r times the same thing, well, actually not the same thing, a n m prime cosine of c omega n m t plus b n m prime sine of c omega n m t. Now let me write this a different way. So I want to write this as the sum from n equals 0 to infinity. This is not necessary, but I think it helps understand it a little bit better. So if I multiply this out, I have 4 terms, but there's a Bessel function jn in every one. So I'm going to write this as jn of omega n m times r. Then I'm going to, this first term I'm going to say it's this cosine times that cosine. So it's going to be, let's call this little a n m. So I'm going to rename my coefficient. That's this guy times that guy. So little a n m times cosine of n theta times cosine of c omega n m t. Now the next term, let me do, how about a sine times this cosine? So plus, I'm going to call that bnm sine of n theta times cosine of c omega n m t. So again, I'm going to call bn this term times that one. And now I have 2 more. So I have a cosine times a sine. So let me call that term a n m prime times cosine of n theta times sine of c omega n m t. And finally, we have product of these last 2 terms, a sine and a sine, plus b n m theta times sine of n theta times sine of c omega n m t. Okay, so 4 different terms. We could break this into 4 different sums if we wanted to. And let's just think about what happens when we plug in the initial conditions. So let me write that down. So let me plug in t equals 0. So let's use the initial condition. U of theta r, all right, I've been using r and theta. Let me switch that. U of r theta 0. And now what happens? So when we plug in t equals 0, this term here becomes a 1. So these cosines become a 1. That's why I grouped them like this. And then these sines become zeros. And so those terms just go away. So look what we get. We get the sum from n equals 0 to infinity and m equals 1 to infinity of, so we have a simple Fourier Bessel series. So we have a n m times cosine of n theta times jn of omega n m r plus this term, b and m times sine of n theta times jn of omega nmr. And we have to set this equal to h1 of r and theta. So if we do this, we know how to do this, just like we did in the previous slide. This a and m, so if I call this guy f and m, I call this guy g and m, then a and m is just the projection of h1 onto f and m. So it's the inner product of h dot f and m over f and m, and b and m. This is just h dot g and m over g and m. We're so used to using these inner products now for, I mean, it almost seems like magic, but remember in the beginning of the class, we learned about linear algebra and projections and orthogonal bases. We derived these formulas. We did it for vectors, and then we moved on to Fourier series, and here we are now. Okay, so we know how to get these ANs. We know how to get these ANs and these BNs. What about these two things here? The A and M primes and the B and M primes. Well, this one I'm not going to do. I'm conveniently out of room, and I can't fit this in the margin, as a famous mathematician once said. But let's just think about what would happen. If you take the derivative of this, what's going to happen? You're going to get these basically the cosines turned into sines. You get out you're going to get C omegas everywhere. The sines turn into cosines, and you get out C omegas everywhere. And then you plug in 0, and the sines, which are now these two terms, are going to go to 0, and these two terms are going to go to 1. Let's see if we can actually do that. So let's plug in u, or not plug in u. Let's plug in t equals 0 to ut. So ut of r theta 0. Let's see if we can do this. So what happens when you take the derivative and you plug this back in? So you're going to get, you're going to get an infinite sum. You're going to get a c times omega nm out because you're taking derivatives of these sines. Again, these two terms you can completely ignore. We take derivatives, they become sines, you plug in 0, they go away. But these two terms, you get a c omega going out. And then you're going to get, so what's going to be left? You're going to get basically the same thing we had here. It's just now you have a prime here and a prime there. So you're going to get a n m prime cosine of n theta times j n of omega n m r plus b n m prime sine of n theta j of n of omega n m r. And so we get, and this thing we have to set equal to h2. So now we know what the a and m's primes and the b and m primes are as well. We know that a and m prime is, well, we had to equate coefficients. So we take the projection of this. Well, so what's the corresponding term on here? That's going to be h. Oh, I put h down here. I should probably say, oh, this is h1, wasn't it? Yeah. So down here, I need to make these h's h1s, and so here I mean h2 dot f n m over f n m f n m. Oh, but hold on, I got to be careful. I'm equating coefficients. So this is the coefficient, corresponding coefficient in here, but now we have the c omega n m. So I got to say c omega n m times this. So we can solve for a and m, and it's just this thing divided by the c omega n m. And similarly, C omega nm times bnm prime equals h2, h2gnm over, let's make that a little better, over gnm gnm. Okay, and we have done it. We have found all of the coefficients using our initial conditions. Let's conclude with a slide that I showed you in the previous lecture, but I think it's worth revisiting it again. These are the eigenfunctions and the eigenvalues of the Laplacian in the unit disk. So we know that the eigenvalues are omega nm squared, and the eigenfunctions are cosine n theta times this Bessel function, Jn of omega nmr, and sine of n theta times that same Bessel function. And here's what they look like. So we saw the heat equation. Given the heat equation, an initial condition with Dirichlet boundary conditions can be built up using a linear combination of infinitely many of these guys. This is what a Fourier-Bessel series is. It's writing whatever the heck, your unit disk is here and you have the heat equation, something maybe, I don't know, something like that, or maybe it's something like a cone. Maybe it's something like sort of a cone type thing. You can build this uniquely as a linear combination of these Fourier-Bessel functions. And then as t goes to infinity, whatever your initial condition is, this dies out, and these things die out because you have that Fourier-Bessel series times an exponential function that acts as a damper. So remember, it was that double sum thing times your a, n, m, f, and m plus b, n, m, g, and m, where those are these guys. But then you had this e to the minus c squared omega n m squared t. And this is the thing that kills everything off and causes whatever your initial condition is, whether it's one of these or a combination of these or something like this, causes the damp out, and heat dissipates and approach the steady state solution of 0 degrees, assuming our boundary conditions are Dirichlet, are 0. In the wave equation, if you start with this one of these same initial conditions and time goes on, then this is going to oscillate back and forth like this, because instead of this exponential function, you have a sum of sine and cosine waves, which is just a shift sinusoid. And that's going to toggle between 1 and -1 for all time. So this is going to vibrate. So compare the wave equation and the heat equation. We've seen it in 1D cases using Fourier series. Here's what it is in the disk using Fourier-Bessel series. I think we're going to leave it there.